All right, let's resume with our lecture one slides. And this is chapter 1 and 2 of your book, if you want to refer to that. All right, we don't have that much, I think, new announcements. Let's see. Today, we're going to learn more about digital circuit design application. We're going to get more sense that basically what is a digital circuit in general. Is that important thing even or not that we want to spend a semester for that? We're going to talk more about hardware structure, and little bit we're going to study more the FPGA architecture, something that the basically main device that you work throughout the semester in your lab. Basically, we're going to see how powerful is that, and we're going to a little bit learn more about Verilog and VHDL, the two main language for FPGAs. All right. Again, grade scope invitation has been sent to you guys. There is no lab or TA office hour and discussion this week. We're going to start all of that next week. But tomorrow, my office hour happens Wednesdays from 12 to 1 at my office, MAB 2124, if you guys want to talk more about that. But the other office hours and labs and discussions is not happening. The instructors, including me and the TAs, we will try our best to respond to students in timely manner. Our timelines would be 48 hours, not including weekends and holidays. So if, again, you need something from us, please make sure that you contact us ahead of time. Like, for instance, like if someone contacts me 10 minutes, 1 hour before the homework deadline and asks me a question, it will be on Sunday. I probably won't get back to that person. I would again suggest that the best way, the easiest way that we can understand what the question exactly is and I can respond is through the office hours. So definitely prioritize attending office hours. But again, email can be the case if the question is not that much complicated, something that we can also answer them. Start the assignments early. Again, we post all the assignments on Sundays or even earlier. And you have at least 1 week for them to start from Monday. Basically, don't let that wait for it until the next Sunday. We won't have any office hour. It would be very hard, kind of, in the weekend. So start early so you can finish up early too. Find the most updated version of syllabus, slides, and everything on Canvas, as we mentioned. Change your Canvas settings so you get an email notification and try to attend the office hours. Any questions? All right. Okay, so our course is Introduction to Digital Circuit Design, correct? Who knows one example of digital circuit design? Or before that, what is a digital circuit? How many types of circuits do we have in general, if we generally speak? So the one type of that definitely is digital circuit. What is the other type? Exactly, analog circuit, correct? What is the main difference between digital circuits and analog circuits? Yes.
A digital circuit is only on or off. That is the analog circuit at any point.
Exactly, yeah. So basically the input of digital circuit is discrete. It's basically what we usually 0 or 1, but it's a binary. However, the input and most of the cases output of the analog circuit is continuous. It's a continuous wave basically that we can get. What is an example of an analog circuit in real application, in real world? Yes. An audio device. Yeah, so basically, for instance, on our cell phone, our transmitter and receiver, what we call it transceiver, that is an analog circuit in general. How do we know that that is an analog circuit? Because when we talk with phone, correct, we hear the voice of person whom we talk to continuously, correct? So it's not like a robot voice, correct? We completely feel that the person is next to us. So in parentheses, why the voice is different through phone, through the actual voice of that person when it's next to us? So you guys have sensed that, correct? So when you talk with phone, when you talk with your friend, the person's voice through phone is different from the when that you are next to each other. You can understand that who's that person is through the voice, but it is a little bit different, correct? Why is the reason of that? Yes.
You speak, it goes into a micro, and that's when the phone presses that signal, and that screws it up. Then it's cellular, which doesn't really screw it up. Digital, you're plugging or screwing it up. Then it goes to the other phone, which converts it to analog. That screws it up. Then it gets played over phone speed. By the time add all those steps, it screws up so much time.
Yeah, exactly. So basically, that's called modulation and demodulation. That's part of that. So the signals, even something as continuous as our voice, cannot be sent in a continuous manner. We need to discretize it, basically, somehow. So we need to convert this continuous wave of our sound to kind of 0 and 1. You need to somehow discretize it. So this transformation causes that it's not the actual signal anymore, correct? So it's kind of a representative of that signal. So that's why basically we can understand that who's that person is, but it's not exactly the same person. So even that one happens through kind of a digital format for sending that, receiving that, then it would get back to the normal situation. That's called analog to digital converter, digital to analog converter, modulation, demodulation, like all of these things that happens in between. All right. All right, now that we know one example of analog circuits, what is an example of digital circuit? Yes. A logic gate, yes, but like in terms of the application, where do I see? We say that, for example, for the analog circuit, that transmitter, right, or amplifier for our voice is an analog circuit. How do I see a digital circuit in real life? Yes. Yeah, calculator is a good example. Yeah, the calculators work with 1 and 0. They are digital circuits. Our computers is basically the CPU is a giant calculator, correct? Yeah, so definitely that's correct. The memory part of our devices, that's a digital circuit. When we say that my memory is 1 GB, what does it mean? 1 byte means 8 bits, okay? 1 gig means 1 billion, okay? So I have storage that I can store 1 billion of 8 bits. 8 billion bits I can store that in that 1 gig of RAM or whatever, all right? I need basically in each of those bits will be stored, it's either 1 or 0, correct? So basically that memory by itself is a digital circuit, correct? Why it is important to learn digital circuits? Because for storing each bit, that we say that in this 1 GB memory, that is nothing now, in nowadays, basically we work with 1 TB or even more than that, basically in our local computers and everything. In that 1 GB, again, we need 8 billion of cell locations for storing these bits, okay? Each bit, we need a couple of transistors for storing each bit. Can be 2, 3, 4, based on your architecture. So we are working with billions of transistors, okay? How easy is to design a 1 billion of anything, of any cells? It's impossible, correct? But somehow it's possible through digital circuit design. So now that we are comparing digital circuit and analog circuit, so we say that for digital circuit, for like a very simple memory, we need billions of transistors, right? how many transistors do we usually use in analog circuits?
Maybe one.
It's a little bit more. So it's usually, it's definitely less than 100. At most, it's basically around 50. But sometimes, yeah, we have RF and analog circuits that work with 4 or 5 transistors. All right. So basically, we are comparing 100 versus billions of transistors. So which field is harder, analog circuit design or digital circuit design? They're both hard in their way. The reason that we can build 1 billion transistors in digital circuits is it's something inherently in that we cannot have that in analog circuits. So they're all hard, or they have their own challenges by themselves. But they are different nature. All right. Okay. Yeah. So basically, our cell phone, our monitors, our display system. So what is our display? What is our monitor? What is our TV display? There we have pixels, correct? That each pixel has for storing 1 bit or 1 byte or something like that, correct? So it's discretized. So basically, it is a digital thing at the end of the day as well. And all of that. So basically, since it has a lot of applications, it is complex, as we talked about that, we require deep knowledge. And that's why we are learning basically this introduction course, and we're going to build based on that and design harder and harder applications. So this is kind of the structure of different components, of hardware components. This is again our FPGA that we use in the FPGA board that we use it basically in the lab. It's hard. Here is the actual FPGA, but there are some peripheral components around that. Okay, so we might have some memory. So this is like a memory module, correct? SDRAM that talk with FPGA. FPGA by itself, we're going to see the structure. It's nothing that much fancy. We might have like 7-segment LED port display. We might have LED. We might have some resistors, capacitors, some input and output. Basically, all of that in general creates our board. This board would be part of our general computer. Correct. So our computer, basically, we have some motherboard that has something, again, like similar structure with this board, but we might have other stuff as well around that. So basically, you can see there's a hierarchy, right? For instance, like this is our memory module. The memory module by itself, again, it has different stuff. There's a different hierarchies, and each of that, basically, we have at some point we reach to that 1 billion of transistors, basically. So in digital circuit design, we have this hierarchy of design. So we're going to see some examples today and throughout the semester, basically, how important is this hierarchical design. Yeah, basically, we reach to this hierarchy. So from transistors, we are building circuits. We are building these logic gates that I think one of the students mentioned today. How many of you guys are familiar with AND or not gates? Okay, that's very good. So these logic gates, they are basic logic gates, right? They are built based on this transistor. So see this example. I have one transistor here. All right. I use this transistor to create one logic gate, maybe a NAND, AND, or XOR, something like that. Then I combine these logic gates to create a logic function. Right? So for instance, one adder. Basically, how I can use these logic gates to create 1-bit adder, that when I get 1 or 0, and the other bit as 1 and 0, I can add them up together. All right. I need multiple of these logic gates for that. So that would be kind of our logic combination. Our logic combination, now I have 1 bit of adder, okay? But how many bits do I need to add properly? Your computers are 64 bits, okay? So I need 64 bits of adders. So now I need to stack these 64 1-bit adder kind of somehow next to each other. That give me 64-bit adder, right? Is that the end of it? No. How about if I need a multiplier? How can I create a multiplier through these adders? I need to stack them, adders basically next to each other. Right? Now I have a multiplier. How can I create, for instance, like a power module? Let's say like 10 power 4 or whatever. I need to stack this multiplier together. Right? So you can see this is a hierarchy basically. The good thing about digital circuit is that this hierarchy doesn't break. I can, when I design something, when I design an adder, almost, not 100%, but almost, it doesn't matter that how many of them I stack them together. It doesn't affect the performance of the next one. Okay? That's why I am able to stack these different things together. Whereas in analog circuits, we don't have this capability. Okay? So for instance, that's basically what I'm talking about is that assume I create an adder here. All right? And then I create another adder here. All right? When I put them together, the functionality of this one doesn't change before and after connecting to the other module. In digital circuits, it doesn't affect that. However, in analog circuits, when I create something here, and when I create another thing here, when I combine them together, the performance of each of them will change. Okay, that's why I cannot stack these together, but I can stack stuff for digital circuits. That's why I can create 1 billion of transistors basically on top of each other and nothing changes, but I cannot work with more than 50 transistors basically in analog circuits. So that's the kind of the challenge. That's the trade-off here. All right. Any questions so far? Okay, so now we saw that all right, digital circuit design definitely needs a hierarchy, correct? We need to build up from logic gates and combinational gates and put them together and create more complicated structures. The analysis of basically this digital circuits also is hierarchical. We can design different parts of this. We need to validate different part of this hierarchy as well. So how user gives us the specifications as engineer? The user will give us, for instance, they say that I need a 1 terabyte memory, correct? That's like how the users will talk to us. They're not going to specify more than that. They are not going to specify that I need 1 billion transistors that they work in a different manner, correct? Users talk in general format, big picture format, correct? That's why this system verification comes in, all right? And again, memory is one part of my general board. I have many other things, correct? So for instance, the user tells us that I need a board that implements, for instance, FFT, okay? So FFT is a function, basically. They need a board from us, they need a circuit from us that basically implements FFT in a very fast or efficient way. Okay? That's the way that users talk to us. It's our job to design different parts of that. So we get this system specification, then we go to architectural design. I need to say that, all right, for implementing that, I need 1 memory. I need 1, for instance, like CPU. I need 1 calculator. I need 1 IO system, so on and so forth. Right? That is basically my architectural design. Then I go to functional design. I would say that, all right, my CPU, my calculator needs to have these specifications. All right, my calculator needs to get, for instance, like I need to have a multiplier. I need to have a multiplexer. I need to have an adder, so on and so forth. Okay. Then I'm going to design each of these blocks, basically. Then, all right, the circuits are designed in simulator, they work, but I need to actually implement that. Correct? I need to actually say that, okay, how exactly these transistors are working with each other. That's where the physical design comes in. Then I actually draw, basically, and implement the circuit by itself. Then I need to verify. I need to verify that, okay, is this giant drawing that has billions of components, billions of transistors actually work before I send it and fabricate it back. Okay? It's 1 billion transistors. Okay? Definitely, I need somehow to verify that there is no short circuit, there is no open circuit, so on and so forth. And more important, it does whatever that I want. So that's where this physical verification comes in. Then I need to take into account some other stuff that I haven't seen in simulator. This is basically when actually some components we put them together. There are many things that we haven't taken care of that in our initial simulation. That's basically it's called parasitic values, parasitic capacitors and stuff. That happens when we actually implement a transistor level stuff. That's why this layout and post-processing comes in. When I check all of that, I need to fabricate that. I fabricate the chip. I send my chip to some of these fabrication company. They're going to give me back. But then I need to package basic and start testing them. That's all of this process should happen that I have one tiny module basically that does, for instance, like a simple calculator. It's a simple calculator or something like that. Okay? And then I put all of them together and we create a different or high level, more complicated board basically next to each other. Any questions? All right. So, all right, what is FPGA? FPGA is a field programmable gate array. We design in Verilog, we simulate and validate that. Basically, it's a way. So we have our simulators, correct? So simulator is the software that we can analyze basically our signals and everything there. But what if I want to really create something that actually it works, okay? So basically assume that, very simple example, that you wanna create a calculator, all right? One way of designing this calculator is in a simulator where we have some software that you can specify input after you design your circuit in any way. You give the actual signal to it, you give the simulator signal to it, input, and you see the output, okay? But what if you really want to see that if this calculator is working in real world, that for instance, like whenever it gives you your correct answer, some LED turns on, or it shows you actually whatever the values in these 7 segments. So basically you want to see that what is 6 plus 4, whatever that it is, you want to actually see it basically that, all right, here it's written 10 basically, right? We need some way to actually implement that circuit. That's where FPGA comes in. For FPGA, we need to describe the circuit, describe whatever that we create in a Verilog programming language, okay? It's a one hardware description language, or HDL. There are 2 famous examples of that, Verilog and VHDL. In this course, we work with Verilog. We need to describe the functionality of our circuit using this language, all right? We write some program, we write some code for that, and then we deploy that code onto our FPGA. Our FPGA actually builds that circuit for us, okay? And then when it builds for circuit, I can actually see that if the circuit is working or not, all right? I can see the actual output. I can give actual input to it. I can give 5-volt input, 0 input, and I can see the output through that. That's why we need an FPGA to actually implement the circuit. FPGA has the structure basically of reconfigurable. It's a reconfigurable hardware. That's why it's excellent for prototyping. Okay. Let's see the next slide. I think it talks better about why that is important. So we have 2 types of hardware for implementation. One of them, again, is called FPGA, Field Programmable Gate Array. The other one is called ASIC, or Application-Specific Integrated Circuit. Both of these ways are for implementing an actual circuit, all right? Both of these hardwares are for that. However, they are inherently different. They are completely 2 different scenarios. FPGAs are reconfigurable with totally new designs. So once you want to create a calculator, you can implement that on FPGA. Once you want to create a multiplier, you implement that through FPGA. Any type of circuit that you want, you can implement in one hardware. All right? We're going to talk about that, how it works in a bit. But it's reconfigurable. You are not stuck with whatever that you have designed, correct? You can easily reprogram it basically and see different stuff for it. So, and it's very cheap, okay? FPGAs are very cheap. However, they are very good for prototyping, for testing basically if something is working or not, when you are in the test mode, definitely you want to design different circuits, correct? You want to see which one works better or whatever. So they're very good for that, but they're not suited for high volume and mass production. It makes them very costly. All right. They are not super efficient because they are working in many fields. They are reconfigurable, so you cannot have a optimized design for that, but it works very well for many scenarios. Correct? However, on the other hand, we have this ASIC, that is application-specific integrated circuit. It's a permanent design, okay? It's tape out, it's functionally cannot be modified, okay? So we have one hand, we have FPGA that is programmable, that is reconfigurable. On the other hand, we have ASIC that it's a permanent design. You cannot change it after when you design it, okay? FPGAs are very cheap. ASICs usually are costly, basically. There are thousands of dollars for having one. So why do we need ASIC design then? If FPGAs is good, if FPGAs are that much configurable, why do we need an ASIC design? Yes.
Because with ASICs, it's very expensive. First one, second one, so bad, but you start.
Correct. Yeah. So that is correct. That is one way of looking into that. The other way is our design for FPGA is not optimized. Okay. So when you wanna implement something, we want to make sure that it's at the most optimized format. So for instance, when you have a calculator, you want to use calculator as a calculator, correct? You don't want to use the calculator as, for instance, like a sensor that detects smoke or whatever, correct? So you can optimize your design in terms of area, in terms of power, everything basically on that calculator, okay? However, in FPGA, your design is not optimized at all. Basically, your memory, the memory that you assign for that, the power that it has requires for computation, is way more than what it needs to be. All right. So basically, what is the best way for handling that? Is when you are in prototyping, you can test your designs using FPGA. Once you conclude that, all right, this design is working, then you can fabricate that chip. You can work on the optimizing that to have the most optimized format. Okay. So basically, that's why we are having these two different things. Both of them are helpful, but in their own way. Any questions? All right. Okay, so this is the FPGA structure. All right. So FPGA is honestly nothing but bunch of switches. All right. So we have these logic blocks. Okay. That again, like we're gonna talk more about that in the class. Right, so we have some calculations stations basically, and we have some connectors that connects these different together. All right. So, for instance, like a very simple way of looking into that, we can assume that all of these are, for instance, like two AND gates. For instance, like some of them is two AND gates. All right. Sometimes in your design, you need one basically block of AND gate. Once you need two, once you need three. Okay, based on these switches that we have here, you can make these connections. You can say that, all right, I need three of them to work in this design. I need two of them, or I need one, or I don't need anything. So with making these switches on and off, we can make different connections basically among these different blocks that we already have. All right, that's why we can, it's a reconfigurable design. All right, whenever that you deploy a new code, the only thing that changes is this connection, is these switches that turns on and off. We don't have to do anything. The compiler does it for us. So the only thing that we need to do is deploying basically the code, the Verilog code. But the Verilog code, whatever that it happens after at the end of the day through the compiler and interpreter and translator, is making these switches on and off. All right, so with different switches that are sometimes on, sometimes off, we can build different circuits. While our structure is the same, our structure doesn't change. Does it make sense? Okay. Whereas for ASIC design, we don't have these switches anymore. All right, we only have these logic gates. It's one way. It's one possible solution then. So definitely, I mean, you can see the difference. In ASIC design, I don't need all of these different logic blocks, right? I need one specific thing, so I can maybe use only 5 of them. But in FPGA, I need to have 100 of them to consider these different scenarios, right? That's why ASIC basically is less power, it needs less area. However, FPGA needs more power, more area, and everything. So it's not optimized, but it's recombinant. Any questions? All right. Yeah, so basically this is again FPGA structure in board. This is kind of the heart of our FPGA. This is this one. Um, this is the actual, all of the calculation or that switch structure that we just saw. This one basically, it's this one. And we have some input, output, and stuff basically that are connected to that. One of them is is a 7 segment that this one makes output 0 and 1, and we can display different numbers basically in these 7 segments. All right. So one thing that we discussed is that we have different HDL, hardware description language. One of them is Verilog, the other one is called VHDL. They both do the same thing, but they're a little bit different. Verilog that we use, it's basically is a syntax is similar to C. However, VHDL syntax is derived from ADA and Pascal. VHDL in general is more used in FPGA, whereas Verilog is more used in ASIC design. However, again, like for the class, we cannot have an ASIC design, so we use it for basically FPGA as well. Both of them works. There's no difference between. Verilog in general is more concise and it's more concise. However, VHDL is more descriptive and less prone to error. Verilog is good preferred for quick prototyping and simple logic descriptions, but VHDL is better for complex design. So they have their own pros and cons, basically. Learning one of them usually is enough. Sometimes some companies work with Verilog, sometimes they work with VHDL. In general, what I have seen, again, Verilog is more popular nowadays. That's why basically we're learning Verilog now. Main strengths of Verilog is its behavioral modeling, and VHDL is supporting hierarchical design. That's why VHDL is used more for complicated design, whereas for one specific design, Verilog usually works well. All right, are there any questions? All right, thanks everyone.